Good afternoon, class. We are looking at Chapter 5, Integrals, Section 5.1 to 5.3, the Fundamental Theorem of Calculus. Chapter 5, Integrals, 5.1 to 5.3, the Fundamental Theorem of Calculus, 5.4, the Substitution Rule. Again, reminding everyone when we were discussing anti-differentiation or integration, since the derivative of kx is k and k is a constant, the integral of k dx becomes kx plus c. Since the derivative of x to the power of n is n x to the power of n minus 1, its integral is x to the power of n plus 1 over n plus 1, plus a constant, of course. N can't be negative 1. We went through the process by explaining that when you take this derivative, you multiply by n, you subtract 1 from it. To do the integration, you do go with the reverse process. Subtracting becomes addition, and multiplication becomes division. And that's where we have the answer. And we proved by differentiating the right side, we should get x to the power of n. If you look at this one, since the derivative of e to the power of x is e to the power of x, the integral of e to the power of x is e to the power of x and a constant. The integral of 1 over x is natural log and a constant. The integral of cosine is sine and a constant. The integral of sine is minus cosine and a constant according to the differentiation. Here's the reverse process. The same thing happens here. Since the derivative of tangent is secant squared, the integral of secant squared dx is tan x and a constant. The integral of cosecant squared dx is minus cotangent x and a constant. The integral of secant x tan x dx is the integral of secant x and a constant. The integral of cosecant cotangent dx is minus cosecant x and a constant. As far as the constant multiple, whether we are dealing with the differentiation or integration makes no difference. If you have a constant, you take it out or you leave it in the integral sign. The sum and difference rules, the same thing for the differentiation. Basically, it says do differentiation as well as integration term by term. The derivative of e to the power of kx, we have to multiply by k. The integration, we have to divide by k. So that's the reverse process. Now, the fundamental theorem of calculus, the method of exhaustion. Areas of familiar polygons such as triangles and rectangles enable us to find the area of more complicated regions by filling the region with increasingly smaller elements of known area. This is called the method of exhaustion. For example, here we use a three-sided figure, meaning a triangle, make it four-sided, five-sided, and as you add to the number of sides, and by the way, you can calculate the area of all of those polygons by cutting them into different triangles or rectangles. And you can approximate the area of a circle. This is before we knew the area was pi r squared. So this is called the method of exhaustion. What if you want the area under this curve? Find the area of the region S that lies under the curve y equals f of x from a to b. This means that S is bounded by the graph of a continuous function f, where f of x is greater than or equal to 0. The vertical lines x equals a and x equals b, and the x-axis. Notice this gives you exactly the same thing. S is the set of points x and comma y such that x is between a and b, and y is between 0, the x-axis, and f of x. So how do you find the area? Well, you can cut it in so many pieces. For example, if I cut this into 4 pieces, and I want to have equal width because it makes it easier to deal with. So this width would be b minus a divided by 4. In general, would be b minus a divided by n. So delta x, so this distance is delta x, everybody. All of this which is the width for this particular question. I cut it into 4, so b minus a over 4, in general, n subintervals, which gives us the Riemann sum. The Riemann sum says the summation of f of x of I times delta x, which means the width times the height, because what is the height of each rectangle? You can choose the left endpoints. If I choose the left endpoints, this one, this one, this one, this one. F of those points, that's why we have f of x of I. They represent the height. This would be a case here. And those are the areas. Okay, so this area plus this area plus this area plus this area. If we go with another point, for example, if we go with the right endpoints, the first one would be this one, the second one would be this one, the third one would be this one, okay, and the last one would be this point. So look at those points first. So the height would be f of those points. So that's why we have f of x of 1 times delta x all the way to the last one, f of x of n times delta x. And that's an approximation. So, by the way, you have all of these examples. Just you want to sit back, relax, and just pay attention to the concept. So this is the Riemann sum. The function f of x is positive on some interval of a to b. Determine the area of the region between the function and the x-axis. So in this case, determine the area between f of x equals x squared plus 1 and the x-axis on 0, 2. In other words, we want to determine the area of the shaded region. If I were to graph this rough graph, is something like this, and this is located at 0, 1. I want to go from 0 to 2. I want this area, okay? Now, to make this nice and easy, let's go just with the shaded region. So I'm going to erase the mess. And so we just want this shaded region. And so we are going to cut it into so many pieces. For example, let's choose number 4. We cut into 4 pieces. And that makes the width, delta x is b minus a, 2 minus 0. This is a, this is b, divided by 4, which gives you 1/2 or 0.5. 1/2 or 0.5. Now let's choose the right endpoints or the left endpoints and work on it. If we choose the right endpoints, these are the points, this one, this one, this one, and this one. That's why we get this rectangle. Okay, this one, this one, and this one. All of them have the same width. What is the area? The width times the height. In this one, we're going to use f of this point, which is f of 0.5 or 1/2. For the second one, f of this point or f of 1. For the third one, f of 1.5 or 3/2. For this one, f of 2. And for example, what is f of 1/2? 1/2 squared is 1/4 and 1/5/4. F of 1, 1 and 1 is 2. 3/2, when you square it, 9/4 and 1 is 13/4. And if you plug in 2, 2 squared is 4 and 1/5. And so this is the area of the first piece, second piece, third, and the fourth. They add up to 5.75. And I'm going to do the same thing now with the left end points. Instead of using these points, now I'm going to use these points for the height. It's L sub 4. And notice that these parts are the same. In other words, for the right endpoints, I didn't use f of 0. For the left endpoints, I didn't use f of 2. Notice that. So these parts are identical. So all you have to do, just calculate f of 0 times 1/2 and add this one to it. And we end up with 3.75. What does it mean? the area is somewhere between the two numbers. As you can see, the area under the curve is larger than 3.75 and it's smaller than 5.75. So one might say, okay, this is tedious. One easy way to deal with, just draw this line segment from 0 to 2 and cut it into n pieces. So 0 to 2, so the first one is a equal to 0, the last one b equals to 2, and then 0.5, 1, and 1.5. And for the right endpoints, don't use a, use this one, and this one, and that's what we did here. For the left endpoints, don't use this. That's all. It's very straightforward, everybody. We're going to continue with the same question. We want to determine the area between f of x equals x squared plus 1 and the x-axis, 0 to. In other words, we want to determine the area of the shaded region. This time we're going to add and use 8 rectangles, in which case b minus a, 2 minus 0 is still 2, but divide by 8 makes it 1/4 or 0.25. So we are making the width smaller. We are going to do the same thing. We're going to go with the right endpoints. And when we use the right endpoints with the concept that I mentioned, just this line segment, to look at this line segment. For the right endpoints, the first one, 0 is not used, but this is used. F of 0.25 or 1/4, f of 0.5 or 1/2 or 2/4, all the way to the end to f of 2. And look at, for example, 1/4, if I put in here, is 1/4 squared, 1 over 16 plus add, which is 17 over 4. You do the math, and you end up with 5.1875. For the left endpoints, we use all of these points except 2. Notice the last one is 1.75 or 74. And again, notice these two are identical. And I mentioned that because it makes life easier for the calculation of this part. All you have to do, f of 0 times 1/4, and then add this part. And it's 4.1875. So the area is somewhere between these two numbers. And you recall when n was 4, the area was between these two numbers. Now, if you look at these two numbers, there's a difference of 2. If you look at these two numbers, there's a difference of 1, which means they are getting closer and closer. And so if you add, it becomes even better. Approximation gets better as n gets larger. And that's the idea. And ultimately, when n goes to infinity, becomes identical to the area under the curve. And so we are going to say, if the function is increasing, and if it's concave up, the right end points will overestimate the area. You see the area of those rectangles seem to be larger than the area under the curve. On the other hand, for the left end points, it underestimates the areas if it's increasing and concave up. So the graph indicates that. All right. The fundamental theorem of calculus. Suppose a continuous function f is defined on the interval of a to b, closed interval of a to b. If the interval is divided into n subintervals, so that delta x is b minus a over n, and x sub 0 is a, x sub 1 is a plus delta x sub 2 is a plus 2 delta x, all the way to x sub n is a plus n delta x, which is b, then a Riemann sum associated with f is the following sum. The summation of I going from 1 to n of f of x sub I delta x is f of x sub 1 times delta x plus f of x sub 2 times delta x, all the way to f of x sub n times delta x, where x sub I is any point in the interval of a sub I minus 1 to a sub I. In other words, it can be the left endpoints, the right endpoints, the midpoints, or any other point. So let's look at the geometry and the procedure called the Riemann sum. Number 1, partition the interval of a to b into a few, say 4 subintervals. Make 4 rectangles. Width is b minus a divided by 4. Delta x is b minus a divided by 4. And then heights are f of x sub 1, f of x sub 2, f of x sub 3, and f of x sub 4. And as we said, it can be anywhere that you choose them to be, the left endpoints, the right endpoints, you name it. Then if you make 8 or more rectangles, the approximation gets better. And as the number of rectangles increase, the approximation gets better. So we can use the left endpoints, the right endpoints, or the midpoints. And again, you don't have to memorize the formula. Just go with the line segment that I showed you. So the Riemann sum represents an approximation of the area. So area is approximated by the Riemann sum I going from 1 to 4, for example, f of x sub I delta x, f of x sub 1 in this case, delta x plus f of x sub 2 delta x plus f of x sub 3 delta x plus f of x sub 4 times delta x. And the area under the curve is exactly the same thing if you take a limit of this expression. Take the limit as n goes to infinity of summation of I from 1 to n of f of x sub I delta x, where delta x is b minus a over n, and x sub I is a plus I delta x. So the approximation gets better as we increase the number n, and it becomes identical to the area under the curve as n goes to infinity. Now, the FTC, the fundamental theorem of calculus, FTC for short, if f is a continuous function on the closed interval of a to b, d dx of the integral of a to x f of t dt is f of x. That means if you integrate the function f of t dt from any number to x, and then you differentiate it with respect to x, you get f of x back. If the derivative of capital F is lowercase f, in other words, capital F prime is lowercase f, the integral of a to b f of x dx, this is a number, is called definite integral. Just evaluate this f of a b minus f of a. If evaluate the antiderivative at the endpoints and subtract them from one another, f of b minus f of a. Now, let's discuss the details for this. This is the sign graph. This is the graph for the sign of integration, the integration symbol. The symbol was introduced by Leibniz and it's called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. A lower limit of integration, upper limit of integration. Here's the integrand and the x. This is the variable that is called a dummy variable because it is called a dummy variable because the answer doesn't depend on the variable chosen. The dx simply indicates the independent variable is x. For example, instead of the integral of a to b f of x dx, this is a number. It does not depend on x. We could use any letter in place of x without changing the value of the integral. For example, I can say f of t dt, the integral of f of t dt from a to b. Its approximation is the Riemann sum of f of x sub I delta x as we go from I to n, f of x sub 1 times delta x all the way to f of x sub n times delta x. This sum is called the Riemann sum. And the precise value for this, okay, which represents the area under the curve if the function is positive, as long as we take the limit of limit as n approaches infinity of the Riemann sum, I going from 1 to n, f of x sub I delta x. We want to evaluate the integral to make sure we understand what we are dealing with. And by the way, we're going to use the concept of area. First, notice there is nothing in front of the x. I put it 1, so I want to mention that the function y or f of x equals 1, which is a horizontal line. That's why I put the 1, so it becomes clear what we have. And we are going to graph that over the interval of a to b, which means there is a horizontal line, y equals 1, and we're going to go from a to b. And this definite integral represents the area of a rectangle of a width b minus a with the height of 1. And you know the area is the width b minus a times the height, which is 1, and you come up with the answer. And the beauty of this is you have a shape, a geometric shape that you can calculate the area because you have a formula for it. But if you don't have a geometric shape that you know the formula for the area, what happens? You can use calculus and the FTC that says if you want to evaluate this, get the antiderivative and evaluate it at the endpoints B and A and subtract one from another. And you don't need the constant because the constant will cancel out. So if one, the antiderivative is x, we're going to evaluate it from A to B. First, you put the upper limit, then you put the lower limit, and the difference is the answer, B minus A. This will always work, whereas this one depends whether you have a graph that you are familiar with or not. Here's another example. Use the signed area interpretation of the definite integral to compute the integral of x dx from -1 to 2. First, what is your function? Y or f of x is x from 2, from -1 to 2. And that y equals x is a line that goes through the origin, 0, 0. And since we want to go from -1 to 2, we mean this area. This portion, because the function is positive, we have it as positive. This portion is negative. And that's why using the signed area means the difference of the two areas. So you find the area of the green, you find the area of the red, and green minus red is the answer. Notice we are using, we are familiar with the shape. It's a triangular shape. Area is 1/2 base times the height. This point has coordinates 2 times 2. So this is a distance of 2. This is a distance of 2. Half of 2 times 2 is 2. For the red one, this one has point -1, 1. The distance of 1, so 1/2 times 1 times 1 is 1/2. And their difference, 2 minus 1/2, the answer is 3/2. So we got the area using geometry, and the shapes, both of them, are triangles and we can handle it. But what if we don't have a shape that we can handle? We go with the definite integral of a to b f of x dx is capital F of b minus f of a. So for this case, if I want to go that route, as you know, the antiderivative is half of x squared, and I don't need to put a constant. We're going to evaluate from -1 to 2. So if you plug in 2, you get 4. If you plug in -1, you get +1. 4 minus 1, this gives you 3 times 1/2 is 3/2. As you can see, it's the same answer. The difference is this will always work. This may not, because it may not be a shape we are familiar with. Finally, for this page, I want you to graph and use sign areas to show that the integral of -4 to 1 6x dx is -45. Here's your function, y equals 6x. I want you to graph it and use this concept to come up with the answer. I'm giving you the answer. Also use FTC, and both of them must result in the same thing. We want to evaluate this integral. Remember, this is a definite integral and it's a number. So x to the power of 7 is 1 over 8, x to the power of 8. We go from 0 to 1. If you plug in 1, 1 to the power of 8 is 1. If you plug in 0, it's 0. 1 minus 0 makes it 0. 1 over 8 in front of it makes it 1 over 8. And I'm going to repeat the tip that I've been discussing. Even if we use another antiderivative, meaning capital F of x plus c, in the evaluation theorem, the result will be the same because it's going to be f of b plus c minus the brackets f of a plus c, and the c's cancel out. That's why we don't do that. The integral of 1 to 2 x to the power minus 1 dx, please understand x to the power minus 1 is the same as 1 over x, and therefore it's a natural log. And of course, in an absolute value, we get ln2 minus ln1. Even if we don't put an absolute value, makes no difference because both numbers are positive. We should know ln1 is 0, so the final answer is ln2, which is a precise answer. Now, if you look at the same question, but different limits that are negative, you must use the same natural log, but definitely with an absolute value. In other words, for part B, if we didn't use the absolute value, it would work. But now it won't if you don't use the absolute value. Because if you don't use the absolute value, ln of negative 1, or for that matter, ln of negative 2, they don't exist, they're undefined. But ln of negative 1, we're going to change it to ln1 because of the absolute value. This one, we change it to ln2 because of the absolute value. ln1 is 0 minus ln2. And bear in mind, this is an exact answer, everybody. The integral of sine x dx from 0 to pi, the derivative of sine is cosine, but the integral is negative cosine x. We don't need a constant. We leave the negative out and we plug in pi and 0, becomes cosine pi minus cosine 0 with the negative sign outside. We should know cosine pi is negative 1 minus. We should know cosine 0 is positive 1. So this adds up to negative 2. Negative outside makes it positive 2.